In this video, we are going to talk about two second-order differential equations that are worth remembering. So the first one is what we call the simple harmonic motion. Simple harmonic motion or simple harmonic model. So what is the corresponding differential equation? For the simple harmonic model, the corresponding differential equation looks like this: y double prime plus k squared y equals 0. We assume that k is positive. So this is the first very important equation, and this model appears in many different situations in engineering and all sciences, and even in like social science and pretty much everywhere. So the question is how to solve these differential equations, and actually we know this equation before when we talk about four fundamental equations. And remember, we had the solution coming from sine cosine, and we wondered like where are those sine cosine coming from. But now we can actually discuss where this that sine cosine terms actually give rise to. So let's look at the corresponding characteristic equation. So the characteristic equation is so what we normally do is we replace the derivatives by lambda powers. So it is lambda squared plus k squared equals 0. And then what we normally do is we can isolate lambda, so we can write this equation as lambda squared, which is equal to negative k squared. And then we know that we can use complex numbers now. So if you use complex numbers, so you can write this one as k squared I squared. So then this can give you the lambda as, once you take the square root, plus or minus k I. So that means you can see that this lambda is a complex number now. So this is complex, and then we can write this lambda in a different way. So we can say lambda equal 0 plus or minus ki. So that means we can write the corresponding equation. So it is yx equal, if you assume x is the independent variable, it is e to the 0, and then you have c1 cosine kx, because that the beta term is k now, plus c2 sine kx. So e naught is e0 equal 1. So that means finally we can write this one. So we can say if we have y double prime k squared y equals 0, so the corresponding equation is yx equals c1 cosine kx plus c2 sine kx. And then you can see that this is where the sine and cosine coming from, because it's a complex solution. So so we're gonna put them inside a box. So that's the first situation. So this is the simple harmonic motion. So for the simple harmonic motion, typical solution is coming from c1 cosine kx plus c2 sine kx, and then we can use the initial conditions to find c1 and c2. So let's look at the second equation. So the second equation is what we call the exponential growth-decay hybrid model. So exponential growth and decay hybrid model. And the reason for this naming will be very clear after we derive the formula. So let's look at the corresponding differential equation. For this one, what's going to happen? There's a slight difference. So it is y double prime, instead of plus put a minus sign. So that's the only difference. So it's k squared y equals 0. We again assume that k is positive. So I'm going to call this is equation number 2. And then again, as before, normally what we do is we look at the characteristic equation. So the characteristic equation is this. You can see lambda squared minus k squared equal to 0. This is very easy to solve. So this lambda equal simply plus or minus k. So that means this is the distinct real root situation. So since this is distinct real root situation, we know that the corresponding equation solution you can write as yx equal a constant e to the kx plus a constant e to the negative kx. So those are the two situations that we get. Now what we can do, so that's a typical solution. So the typical solution looks like that. But if you look at the two terms, you can see that one is exponential growth and one is exponential decay. So so let's look at those two graphs, how it behaves. So so the first one, so the first graph, so it's a k, so we know that k is positive, so that means it's going to grow. So that typical solution looks like that. So where c1 is that's c1, where the curve passes through the y-axis, and for k negative it's going to decay, so that means it's going to go like that. So that's the c2 constant. So you can see that one is exponential growth and the other one is exponential decay. So that's the exponential growth function. This is the exponential decay function. Okay, good. And then also we can do some kind of simplification here. Sometimes those are important in applications. For example, we know that so you can say since cos, so the hyperbolic cosine x is equals to e to the x plus e to the minus x over 2, and sin hyperbolic sine x is equal to e to the x minus e to the minus x over 2. So what we can do is you can rewrite the solution in several different ways. For example, these are other ways to write the same solution, but you will get different constants. So for example, you can write this solution as d1 cos kx plus d2 sin kx. So that's one way to write it. Also you can combine the two type of functions. So for example, you can write this one as a e to the kx, and one of these, for example, you can say b cos kx. So all these solutions are equivalent. One of the reason is all those functions are linearly independent. So if you get the set, you can see that they are linearly independent. The first two is linearly independent, and also the bottom two is linearly independent. But if you take any three, they are linearly dependent. If you take any three, they are linearly dependent. Because of that, you can replace one function from another function because they are linearly independent. So there's a relation between them. So you can use the relation to remove one of the other variable. But there are other ways. So there are actually 6 different ways to write the solution. So so I'm right. So there are 6 ways to write. There are 6 ways to write the solution. It's kind of interesting. So why don't you write those all those 6 different forms? Okay, good. Now let's look at how the typical solution looks like when you graph it. So you can see that if you look at the so the first graph is the graph of the simple harmonic motion. And so what's going to happen if you try to solve for initial conditions? So this is what you get, and the typical graph looks like that. And you can see that it is a combination of sine cosine function, and you know that if you have a sine cosine function like that, you can represent the sum as a single function. So that's like another thing that you can see. You can write this whole function as a single function. So for example, the first one you can write as for some constant, let's say cosine 2 times, so you can say 2 times x plus alpha. So you can write it like that, and because of that, and you can see this is just a cosine function or sine function, and so that's why you're gonna get this kind of graph for that, because you can always rewrite a combination of sine cosine as single function, either sine or cosine. So the goal is to find a and alpha. So that explains why the graph looks like that. So this is the simple harmonic motion. And then for the decay model, so the growth decay model, growth and decay. So you can see that it's hybrid, so you have both in one. So there's a decay part and the growth part. So this is how a typical growth decay model looks like. So in one side it's gonna explode, like it's gonna grow indefinitely. The other side is depending on how far we go, it can even be exploding for negative values because of the negative exponent. So this is a typical graph looks like for the growth model, and this is a typical graph looks like for the simple harmonic motion.